Welcome to Algebra 2. This is section 4B.2, finding possible zeros of polynomial functions. So what we've uncovered so far is we've learned how to factor back in the first part of chapter 4. And then yesterday we learned the fundamental theorem of algebra and how that kind of leads us from factors into solutions. And that's the ultimate goal of this section, is that we start solving these polynomial functions. And there are just a lot of little things. This work was all the rage of Europe in the 1600s, was figuring out all these things about polynomials. Now we get to learn it all in a very short amount of time in an Algebra 2 class. It's pretty cool, the history that goes into this. So today what we're going to look at is how to find possible zeros of polynomial functions. How can we make really good guesses on what zeros will occur within a polynomial function? So let's take a look. So first, we're going to introduce this topic by finding the zeros of a very simple polynomial, right? This is one that we solve by factoring, and we may notice that the solutions are fractions, but where did those come from? In other words, is there a way that I could look at a polynomial and try and figure out what the possible solutions could be before we actually dive into the work? So let's see, we've got 4x squared minus x minus 14, and if we're going to solve that by factoring, we'll set it equal to 0. And we're going to use our magic numbers. Now again, this is something that we covered exhaustively at the start of chapter 3. So we get a negative 56. We find that our magic numbers are then a negative 8 and a positive 7. So I want to make my outside product, let's make that outside product be 7. So I would have 1x times a positive 7 to make that happen. First times first had to make 4x squared. That means that has to be 4x. Last times last had to make negative 14. So there we got a negative 2. Okay, so that equals 0. Let's see what our solutions are. We could have had x equals 2, and we could have had x equals 7 over 4. So the idea is that there's a great pattern that comes out of this. So where did those solutions come from? Well, when we took a look at each factor and we set that equal to 0 and solve, take a look at what happens. We have this 7, and if we were to follow that all the way back to how we got that 7 in our factor, it was a factor of 14. And then when we divided by 4 to get our solution, where did that 4 come from in our factor? Well, it was a factor of our leading term, 4. So as we go through this factoring process, we're actually rifling through some of the possible solutions that could occur. So looking at the constant at the end and the leading coefficient at the beginning leads us to some possibilities for answers. This does have a name. It's called the rational root theorem. And if we have any polynomial, it doesn't just have to be a quadratic. That was just my example to introduce. But if we have any polynomial with integer coefficients, every rational solution, everything that we could write as a fraction, is found by a factor of the constant at the end over a factor of the leading coefficient. So this theorem allows us to figure out what possibilities we could have that are rational number solutions. All right, and then underneath the irrational conjugates theorem, again, that's just a repetition of what we talked about in our fundamental theorem of algebra. Just a reminder that if we have a plus root b being a solution, then a minus root b is also a solution. And we may see that show up at the end of the lesson. All right, so example 1, list. List. We're not actually solving anything yet. Remember, we're looking for possibilities. So all possible rational zeros. My eyes drift instantly to the constant at the end. Factors of 4 are 1, 2, and 4. And the leading coefficient at the very beginning. Factors of 5 are just 1 and 5. So I want to think of every possible combination of a factor of that constant at the end over a factor of that leading coefficient. And just because of the natures of reflections and things like that, we want to incorporate either the positive or negative variance there. So these possible zeros are plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 4 over 1, plus or minus 1 over 5, plus or minus 2 over 5, and plus or minus 4 over 5. You can see all of those fractions were found by taking a factor of the constant over a factor of the leading coefficient, either something 1, 2, or 4 over 1, something 1, 2, or 4 over 5. So those are all the possible rational zeros, all 12 of those that could show up. Letter B, plus or minus, let's see, my constant at the end has factors of 1 or 3. My leading coefficient has factors of 1, 2, and 4. So plus or minus 1 over 1, plus or minus 3 over 1, plus or minus 1 over 2, plus or minus 3 over 2, plus or minus 1 over 4, plus or minus 3 over 4. So each time taking those factors of the constant over the factors of the leading coefficient. Now, it is possible that we got lucky here with some prime numbers showing up along the way, but it is possible as you go through these that you do have answers that show up more than once in your list. So, for instance, if, say, when I did 3 over 2, maybe that was a 6 over 2. Well, I've already said plus or minus 3, so you don't have to count that again. However, I do want you to appreciate the pattern and where it's coming from. So realize that your list may have some duplicates in there. That's totally fine. Next, aside from just what are rational solutions, there are some theorems on how many zeros we could have. All right, so Descartes' rule of signs. Descartes was a pretty big thinker when it came to polynomials. Actually, every time we graph something on the xy plane, it's called the Cartesian coordinate plane. It's named after this guy. So every time we have a term in a polynomial that switches from a positive term to a negative term, that's a chance for that sign switch to cause the graph to cross the x-axis. And so what we're looking for is sign changes in a polynomial to determine the possibilities. Okay? Now, we're dealing with positive x inputs when we look at these sign changes. So if I want to look at the possible negative zeros, I would simply switch the sign on all the x terms. So there's one little saying that I want you to take with you. And that's that even powers absorb negatives. In other words, if I had an x to the 4th power and I substitute that x with a negative x, the even power would absorb the negative. It would still remain a positive x to the 4th term. All right? Now, there's a little bit of explanation that goes behind this. And so I want you to imagine that we're looking at a polynomial just on the positive side of the x-axis. So we've got some polynomial that bends like this. Okay? And so if we run through our Descartes' rule of signs, we could find that maybe this graph bends low enough, the terms are strong enough to cause 2 crossings. Maybe they caused no crossings, and just maybe it was enough to just brush the x-axis. Either way, our gain is 2 solutions because of that multiplicity, that husband, wife, brother-in-law. So with Descartes' rule of signs, when we count the number of sign changes, and say we get 6 sign changes, that means there could be 6 real zeros that are positive x's. But maybe it wasn't strong enough, so maybe there would only be 4 or 2 or 0. Once we find the number of sign changes, we count down by 2. So that might be the other thing we want to say. And again, examples will clear this up greatly. All right, so we're going to use Descartes' rule of signs to find the different possibilities for real positive, real negative, and imaginary zeros of the polynomial. Okay? So off to the side, we're just going to make a little table here. And this is kind of cool. This is math that's pretty straightforward. We're not actually solving anything, but when we come out of it on the other side, we're going to have a much greater understanding on how this all ties together. And I think that's a big thing you want to take away. All right, so first, in letter A, let's look at the sign changes now. I've got a positive 3x to the fifth. When I move to the next term, there's one sign change. Then I go from a negative 2x to the second to a positive x, there's a second sign change. From a positive x to a negative 1, there's a third sign change. So positive zeros, I could have 3, or I could have 1. We counted down by 2, and then obviously we can't count down by 2 any further. Now to find the negative zeros, I'm going to look at r of negative x. Well, 3 negative x to the fifth, that's an odd power, so the negative sign is not absorbed. It sticks. Negative 2 times x to the second, well, that second power will absorb the negative sign. That term doesn't change. Next, positive x. If I replace that with a negative x, and then obviously minus 1, there's no x there, so it doesn't change sign at all. So let's see here, I go from negative 3x to the fifth to negative 2x to the second, no sign change there. Negative to negative, negative to negative. So possible negative real zeros are none. So now why did we make that table off to the side? Well, one possibility was that I had 3 reals that were positive, or I could have 1 real that was positive. Possibilities for real negatives, well, there were no real negatives. And so that means for imaginary zeros, because it was a 5th degree polynomial, if I did have that first line, 3 real positives, that means 2 had to be imaginary. Or if I had 1 real positive, I would have 4 imaginary solutions. So you can see just by looking at the signs in that polynomial and kind of looking at how those change from one term to the next, we can get an idea of what our solutions should look like. All right, let's take a look at letter B. We're looking for positive zeros first. I did not get a sign change first to second. Those are both positive terms. Ooh, I do get a sign change there, positive to negative. Ooh, second sign change there, negative to positive, and then positive to positive. Okay, so we only had 2 places where our terms changed sign. We could have 2, or we could have 0. And then I can't count down by 2's any further than that. Okay, let's look at t of negative x. That will point out our possible negative real zeros. Let's see, we got an x to the 18th, so that term does not change its sign. An x to the 4th does not change its sign. X to the second does not change its sign. That positive x will turn into a negative x, and then plus 3. Yeah, remember, even powers absorb negatives, so if a term has an even power on its x, it's not going to change sign from what was in the original function. Let's count the sign changes. No change there. There we have 1 change. No change there. And there we have a second change. So for negative, we could have 2 or 0. All right, so if I set up a duplicate chart over here, real positive, real negative, or imaginary, how could the zeros lay out in this problem? Well, I could have 2 positives and 2 negatives. I could have 2 positives, 0 negatives. I could have 0 positives, 2 negatives. I could have 0 positives, 0 negatives. Lots of possibilities here. This is an 18th degree polynomial, so if I had 2 positives and 2 negatives, that still leaves me with 14 solutions by the fundamental theorem of algebra that could be imaginary. If I had 2 positives and no negatives, that leaves me with 16 imaginary solutions. Likewise, if I had 2 positives or 0 positives and 2 negatives, it leaves me with 16. Or there stands the possibility that I have no real positives, no real negatives, and all 18 of those solutions are imaginary. So again, the purpose of this exercise, is it useful in a practical sense nowadays with all the technology that we have in graphing really quickly with calculators and all that good stuff? Not really, but that doesn't mean it's not important logic to go through. And there's still some important connections to draw. That's why I think this is still an important concept to cover. Very, very neat. And our final key concept of the day, how can we use symmetry to our advantage? And there is a way of classifying functions as either even or odd functions. A function's even if f of x is equal to f of negative x for every x. So that means a parabola is a really good example of an even function. If I go out to some x value and have some height there, then if I go to some x value the same distance but in the negative direction, I'm going to get the same height. F of positive x gives me the same output as f of negative x. And if that happens for every height that we see, maybe this one is down here again. If that happens for every height, what we get is a graph that is symmetrical about the y-axis. Right, so that's an example of an even function, because every time I go to a positive x, the height there is the same as if I went to the negative version of that x. And if I consider an odd function, that means if I go to some x value and find a height there, if I go to the opposite of that x value on the other side of the y-axis, I will get the opposite height coming out. And so again, if I have this happening on my curve, what I'll see is a graph that looks like this. It shows symmetry through the origin. Okay, so here's an example of an odd function. And these provide some really cool patterns as well to add to our ever-growing library. What we're going to do is we're going to wrap this in with solving, because it's going to be kind of a what do you notice type of thing. So determine whether the function is even, odd, or neither, then find all the zeros by factoring. What do you notice about the zeros in even and odd functions? So if I want to test if it's even, that should always be my first test. I'm going to see what happens when I plug in a negative x. This is very much like Descartes' rule of signs. Odd powered terms will switch their sign when I plug in a negative x. Okay, now does this function that I just came up with, did that match the original? In other words, did that f of negative x equal the original f of x? No, and that means it's not even. Right? Well, now let's find negative f of x. In other words, what happens if I distribute a negative into the original? Well, then I would multiply negative onto 2x to the third, multiply negative onto 8x. Was that a match to the one before it? In other words, did this negative f of x equal f of negative x? Yes. So it's an odd function. So what we're going to do is with this odd function, we're going to find the zeros using our factoring techniques. So 2x to the third minus 8x, where would that equal 0? I know it's a third degree, so I should have 3 zeros showing up. Here I can take a GCF. We should always look for that first, of 2 out. I get x squared minus 4. Oh, and what's left behind is a difference of perfect squares. So that x squared plus 4 factors out to x plus 2x minus 2. And I find that the zeros are x equals 0, negative 2, and positive 2. And we're going to save that what do you notice until after we've done all 3 of these problems. All right, Next, letter B. This is the form of a quadratic. X to the fourth minus 13x squared plus 36. Let's test if it's even. Even powers absorb negatives. And I guess that's 36. There's no place for a negative x to change that. It's just a 36 constant. Does that match the original? Yes. So this is an even function because it's a perfect match when I plug in a negative x. All right, so let's find all the zeros by factoring. So x to the fourth minus 13x squared plus 36 equals 0. I know because it's a trinomial with x to the fourth that these are both be x squared. And minus 9 and minus 4, those magic numbers allow us to factor that. Furthermore, each one of these factors, x squared minus 9 and x squared minus 4, is a difference of perfect squares itself. So I find that my zeros are x equals 3, negative 3, 2, and negative 2. All right, that's interesting. And lastly, letter C. The only hope I have at factoring a four-term polynomial is by grouping. Let's test if it's even or odd first. So if I plug in a negative x, odd-powered term, even-powered term stays, odd-powered term changes, and constants, well, they're constant, they don't change. Is it an exact match to up above? No, so it's not even. Let's try distributing a negative into the original. That changes everything's sign. Is that an exact match to what was up above? No. So this is neither even nor odd. So let's find the zeros by factoring. If I factor by grouping, I will group the x to the third minus 2x squared. Again, that's my only hope for a four-term polynomial. I got a negative 4x term and a positive 8. Out of the first grouping, I can take out an x squared. Out of the second grouping, I can take out a negative 4, and notice that leaves behind matching parentheses. And since we're finding zeros, I'll set it equal to 0. I got x minus 2, then x squared minus 4, which is x minus 2 times x plus 2 times x minus 2. That x squared minus 4 is a difference of perfect squares. So my zeros here were x equaling positive 2 and negative 2. However, that positive 2 had a multiplicity of 2. If we think about husband, wife, brother-in-law from the last section. So what do I notice? What do I notice about zeros in just the even and odd functions? Well, there's a symmetry there. Just like the graphs themselves showed symmetry, so do their zeros. So this first one, letter A, was an odd function. Think about plotting those zeros on the x-axis. We had 0, positive 2, and negative 2. Those show symmetry through the origin. Likewise, in the second example, we had negative 3, negative 2, positive 3, positive 2. Those solutions are symmetrical just like the graphs would be. And the last one, I should point out that although this one happened to show that same symmetry, in other words, we had negative 2, we had positive 2, the graph itself is not symmetrical. So this is kind of a coincidence that at positive 2, we had a touch point in the graph. So even though our solutions happen to show symmetry, the graph itself would not. So you cannot assume with a neither function that you'll have this every time. However, if your function is even or odd, you know that your solutions should show that symmetry. right, that wraps up this lesson, 4B.2. Hope you've walked away with something today. Very cool stuff about polynomials.